Let's go ahead and finish off the material with some applications, some quick applications of exponential and log equations here. So let's look at some application problems. Let's look at some applications of logs and of exponentials and logs. Of exponential and log equations. All right. One particular application I want to get at is the compound interest application, because often we have our money in the bank, and our bank pays what's called compounded interest. All right. So let's take a look at those concepts here. Now, what does that mean, compounded interest? Look at the compound interest formula. Compound interest formula. Compound interest pays you interest on top of interest. All right? In other words, if you leave your interest in the bank, you can make interest on top of that as well, all right? Which is a good deal, all right? Which is different from simple interest, which you've seen in a previous math class, for example, right? So compound interest is what we want, and that's what all the banks pay. All right. Anyways, here's the formula for that, right? So here's the formula for compound interest here. So this P is equal to A times 1 plus I to the nth power. All right. Let's explain what these variables are. Right. Now, P is the value of our investment after our interest is compounded for that long, n. So first of all, let's talk about n. N is the number of compounding periods. Compounding periods. In other words, how often the bank credits interest to our accounts. All right. Most banks credit interest to our accounts on a quarterly basis. So we'll do an example on that in a moment. All right. But this is number of compounding periods. I is the annual interest rate. This is the annual interest rate. All right, such as 3%, 8%, whatever the banks are paying at that particular time. A, first of all, is the how much money we're putting into the account. This is our principal, basically. So maybe P and A are kind of confusing in that sense, but yeah, A is the principal, or I should say, how about the initial investment? This is our hard-earned money. Right? This is our money that we're putting in. Let's say I'm putting money into a CD account, $3,000. Then my A is $3,000. All right. So, for example, this is my initial investment into the account. All right. That's called a principal. All right. Now P, which is not the principal in this case, right? For this, oh, sorry for the confusion here. P is the value of the investment after n compounding periods. So let me get my sketch pad to work again. Sorry about that, guys. Give me a moment here. Okay, sketch pad's working again. So again, P is the value of the investment after n compounding periods. In other words, if we're paid interest a certain number of times, then this is how much money we're going to have in that account. All right. So let's take a look at a problem involving these concepts, this equation here. Again, keep in mind this is the value. This is the final value of my investment after this number of interest payments. Right. This is the number of interest payments, basically. Right. A is the how much money I'm putting into the account, my initial investment, or the principal we call. I is the interest rate that the bank is giving me, for example. All right, let's go and clear out the screen. Let's go and try this problem out. All right, so let me go and get this problem on there. All right, so there it is. Let me go let me center it properly. All right, so. All right, so here's the problem that we're looking at here. So Jeff invested $5,000 into a Roth IRA CD. So we should start some kind of Roth IRA account. because the investment will grow tax free, which is good when we take it out later on when we retire, for example, right? That earns 5% annual interest compounded quarterly. So keep that in mind, compounded quarterly, right? This is most banks pay quarterly interest, or basically every 3 months, if you will, right? What is the value of the investment after 3 years? So I'm getting 5% interest on a quarterly basis, right? I'm putting in $5,000 in terms of what Jeff's doing, right? So let's write down our formula again. So P is equal to I should say, times 1 plus I to the nth power, right? First thing we got to determine in this problem is the number of compounding periods. In other words, how many interest payments is the bank going to make in 3 years' time? Well, now quarterly, that means what? That means that the bank pays 4 times per year, right? And for 3 years, then my n is going to be what? 4 times what? Times 3, or 12 compounding periods. There's 12 payments of interest here, right? 12 compounding periods in 3 years. If the account pays quarterly, right? Pays interest quarterly. So n is equal to 12 in this problem, right? What's I? Well, I is the what? Annual interest rate, but I need to break it up a little bit, right? So actually, so maybe I isn't quite the annual interest rate. So I apologize for that. Yeah, so I is actually the interest rate per compounding period, actually. So sorry. So earlier I wrote down annual interest rate, so that's not correct, right? So I should be the interest rate. Let me fix that here. Interest rate per compounding period. Now, what does that mean, per compounding period? So since the annual interest rate is 5%, right? Again, that's not my I right here, right? I is the interest rate per compounding period. So sorry for the confusion earlier. All right. So we need to divide the 5% by what? By 4 in this case, because the interest rate, there's 4 compounding periods, right? And so this is the annual. This is the interest rate per compounding period. So I, in this problem, is going to be 5, or 0.05, if you will, right? 0.05 divided by 4. All right, let's punch out the calculator here. So we're going to get 0.05 divided by 4, get 0.0125. So this is going to be 0.0125. All right, dividing 0.05 by 4 again. 5%, that's 0.05. And again, I is what? Sorry for the confusion earlier again. This is the interest rate per compounding period. Right? This is how your your textbook defines the I here. So just read up on your text on that if you find all this confusing. So I apologize again. All right. But anyways, so that's what I is. We're going to take the annual interest rate divided by 4 because we're compounding it quarterly. So I is 0.0125 when you punch it into the calculator. Now my A is going to be what? Well, obviously, Jeff's investing what? $5,000. That's his initial investment, or his principal, if you will. All right. So let's calculate the amount that he's going to have after 3 years using these 3 numbers by just plugging in here. No big deal. So 5,000 times 1 plus 0.0125 to the 12th power. All right, n is 12 in this case, right? So this is 5,000 times 1.0125 to the 12th power. Let's punch this number into the calculator here. So we're going to get, now punch this into the calculator first before you multiply by 5,000. So I'm just going to do it all in one shot. So use the power button for this, all right? So let me go and do it all in one shot here. So 1.0125 to the 12th power. Now that's roughly 1.16, all right? But I'll multiply it by 5,000. All right. So after 3 years, the total value of the account is going to be roughly, since I'm talking about money, it's rounded in terms of cents, $5,800, $803, I should say, excuse me, and 77 cents. All right. So this is the approximate amount, $5,803.77. So he's going to make about over $800 in interest over 3 years if it's compounded on a quarterly basis at 5% annual interest. All right? So that's just one application using this exponential equation for compounding interest here. So and there are more problems on this in the text for the homework. All right, let's try another problem here. Let me go and clear out the screen. Let's go and try this problem. All right, let's go and try this problem right here. All right. All right, so let's take a look at this problem here. So the current in amps in an electric circuit, so electric circuit problem is, so electricity here, right, is given by I equal to 6 times the quantity, 1 minus E, this is the natural number, right, e to the negative 2t. So this is related to natural log, obviously, right, where t is the time in seconds. Based on this equation, after how many seconds is the current going to be 4 amps? So in other words, based on this equation, let me go write the equation again. So I is equal to what? 6 times 1 minus e to the negative 2t. T is in seconds here, right? Now, I is the amperage, right? The amps. So what's my I here? Well, that's going to be what? 4 amps. This is my I. All right? So I'm going to plug in, so in other words, I is equal to 4 in this problem. So let's plug it in for the I. So we're solving for t because it says based on this equation, after how many seconds, right? That's what t is, right? With the current going to be 4 amps. So 4 equal to 6 times the quantity 1 minus e to the negative 2t. All right, let's solve this equation for t. How do we do this? We'll divide both sides by 6 first. Okay, so we need to be able to solve this exponential equation, right? 4 over 6 is 2/3. I'll just use fraction instead of decimal, 0.66, repeating decimal here, right? But we're not going to use decimal. I'll just use the fraction if you don't mind, because I can punch that in using the calculator, certainly using the fraction key. All right, 1 minus e to the negative 2t. How do you solve for t? First, let's subtract the 1. Let's get the 1 over to the other side. 2/3 minus 1 is going to be negative 1/3. If you punch out your calculator or do it by hand, doesn't matter. Negative e to negative 2t. All right, divide both sides by negative 1. Divide out the negative there. And that will be positive 1/3. So let me continue here. So we get positive 1/3 equal to e to the negative 2t. All right, how do we solve for t? Well, this is base e, right, the natural number. So this is related to the natural logarithm. So take the ln of both sides to solve for t. So let's take the natural log of both sides, ln of 1/3 equal to ln of e to the negative 2t. Now this exponent by the power rule will come out to the front when I do that. So you get ln of 1/3 equal to a negative 2t ln of e. But what's ln of e? Well, that's just 1, right? Because a natural log of a natural number is just itself. It's 1. It's the number 1. There's e to what powers it's itself? 1. All right. So this equation is nothing more than ln of 1/3 equal to negative 2t. So just divide by both sides by negative 2 to finish the problem. So let's go and see roughly how many seconds will take for the amperage to get to 4 amps. All right, let's punch out your calculator. So 1/3 fraction key, using the fraction key to enter that fraction key here. So natural log divided by negative 2. I get roughly 0.55 seconds. So roughly half a second, a little bit more than half a second. So roughly 0.55 seconds will the current get to 4 amps based on this equation here for this electric circuit. All right. So here we have electricity application with this exponential equation right here. All right. So let's finish out with the log equation here to wrap things up. So pretty short section here on the applications, but certainly we can. There are more problems to do on the homework on that. All right. So let's go ahead and let me go and clear off screen and try a logarithmic application here. Go and clear off the screen. All right. So let's try this one then. All right, so let's take a look at this problem here involving a log equation here, if you will. All right, so let's take a look at this application here. So the number of decibels, d, of a sound. So decibels is so sound is measured in terms of decibels, right? You might have heard that somewhere before. But anyways, it's given by this equation: d equal to log. I'm sorry, not log. 10 times the log, I should say, of I plus 16, all right, where I is the power of a sound measured in watts, all right, so I is the intensity of the sound measured in watts. Suppose the power of a sound is 630 watts, find the number of decibels. So it's a pretty simple problem. Basically, you're given the I right here. This is my I. right? So I is equal to 630. Just plug it in to get the number of decibels. So this is going to be 10 times log, what's the base of this? Common logarithm, right? No, if it's not stated, it's base 10. So use the log button on your calculator. Log of what? 630 plus 16. All right, so let's take a look at this solution from the calculator then. So this is going to be what then? 10 times what? Let me punch in the calculator. So 10 times roughly, if I punch in the calculator, 630 log, all right, plus 16. All right, so this is roughly 18.8, I'll just say, on a calculator. So roughly 18.8 on my calculator. So this is going to be 188. If the power of the sound is 630 watts, the number of decibels, the decibel measurement of the sound is going to be what? 188 decibels here. So this is going to be 188 decibels, if you will. Let me get my sketch pad back to finish this off. Apologize, guys. Okay, so 188 decibels. Now there are many other applications of exponential logarithmic functions here and equations here, right? Ranging from exponential growth and decay to earthquakes, study of earthquakes, and what have you. So there are many applications. Again, take a look at those on your homework, obviously. Right? There are no postings for this particular section, so just a real short section on applications. So